Greetings, ladies and gentlemen. Welcome to the portal. Okay, guys, today's lesson it will be focused on acid-base reactions in aqueous solutions. Okay, so we will once again talk about balancing the acid-base reactions in aqueous solution. I've spoken about that, I think, in the previous videos, but I will touch also a few things in this video regarding acid-base reactions in aqueous solutions. We'll also look at how to prepare a standard solution, the procedure that is required for you to prepare a standard solution, and we'll look at how do we dilute a solution that we have prepared, and then also we will perform calculations involving dilutions. Okay, so let's get to it, guys. Okay, so let's start with number one: acid or base reactions okay, in aqueous solutions. Okay, so now it means now if I have an acid, I add my acid to water. What am I having? I have an acid and a base. Okay, so now I'm going to have this the product will be what? Hydronium plus what? Plus A minus. How do I know that I have hydronium and A minus? Well, it's because according to Arrhenius said that when we dissolve an acid in water, the concentration of the hydronium ion will increase in water, or we can say that the hydronium ion is being produced in water. Okay, guys, so now this is just a general equation of any acid. So now if I can take different examples, I can start with example 1. I can start with HCl, which is a monoprotic acid. Okay, what is a monoprotic acid? It is an acid that can donate only one proton. Okay, so this is what I'm getting here in Cl minus. Okay, so always write states here. Okay, the state of your ions and other compounds. Okay, so now you notice most of the time I don't write the states because they just consume time. Okay, but you must write the states. Okay, so now this is monoprotic acid. Okay, so now let's try a diprotic acid. We can try H2SO4 plus water to give us what? To give us hydronium plus SO4 2 minus. So if you can check if we can try to balance this equation, we can balance it easy like this. Sulfuric acid is a diprotic acid, right? So it must donate 2 protons. How do we know that it will donate 2 protons? Because we can see its conjugate base, that is what? Is sulfate. So it has donated two protons to become sulfate. So if it donates two protons, those two protons, they must be accepted by water molecule, right? So but one water molecule cannot accept two protons at the same time. Okay, so it means now we're gonna need two molecules of water so that each can accept one proton of hydrogen. Okay, one proton. And then now if two of water molecules accept two protons, therefore two hydroniums will be formed, so that way it is balanced. Okay, you can continue to check it. Okay, thirdly, let's try phosphoric acid. Okay, so phosphoric acid is what? Phosphoric acid plus water giving us what? Hydronium plus phosphate ion. Okay, so now phosphoric acid can donate up to 3 protons, so it is a triprotic acid. Okay, so this one is diprotic, and this one triprotic acid. So this phosphoric acid can donate a maximum of 3 protons, and for it to become phosphate, so it has donated 3 protons, so it means 3 water molecules must be present to accept the 3 protons from the phosphoric acid. So and if we have 3 water molecules, we will have 3 hydronium ions. Okay guys, simple as that. So if you have a diprotic or triprotic acid, you must check whether how many protons can that acid donate. If that acid can donate 2 protons, therefore on water you will put 2, and when you put 2 on water, water goes with hydronium. You put 2 on water, you put 2 on hydronium. Okay, and if you have triprotic can donate 3, and if it can donate 3, it means you're going to need 3 water molecules, and if there's 3 water molecules, there must be 3 hydroniums. Okay, so yeah, that's all there is to it. And then number 4, let's try a base in solution. We can try ammonia in water. Okay, ammonia in water. What happens when we add ammonia to water? Ammonia is a weak base, right? So what happens is that ammonia is going to take a proton from the water molecule to form what? To form ammonium ion, to form NH4 plus, right? Plus OH minus. Okay, so let's have another example of a base. Let's take sodium hydroxide in water to form what? So sodium hydroxide in water, what is it going to form? It's going to form, it's just going to dissociate. There won't be any reaction of sodium ions or hydroxide ions in water. So here we'll have Na plus what? Plus OH minus. Okay, so plus plus water. All right, so and then now water cancels water. Okay, water can cancel out because we have water on the left and water on the right, so we'll end up with what? Sodium hydroxide giving us what? Giving us Na plus plus OH minus. Okay, so now others can argue and say that but if this is a base and this is an acid, there must be some sort of reaction. Well, let's do this. So the Na, when it separates from the OH minus, we get the we get this, okay? And then now there's a water molecule, you see. So if this OH minus takes this H, I'm going to be left with another OH minus. So it's like nothing happened. So that's why I say there's no reaction between the sodium hydroxide and water. So there is no ionization, but there's only dissociation, you see. So yeah. Okay. So that's all there is to it, guys. We just have to know how to balance the reactions of acids and bases in solution. Okay. So now I can write the last one that they can ask you about. Okay, calcium carbonate in water. Okay, I like this one. Even though it's not in water, but maybe calcium carbonate with HCl. Okay, so but here calcium carbonate with water. So also, what are you going to check here? A carbonate ion has ions of what? Of has ions of -2, charge of -2. Okay, so calcium it has a charge of 2, and then carbonate has a charge of -2. Okay, so now it dissociate and then it will ionize. So let's see what is going to happen now. So this will require 2 protons. Okay, so because it requires 2 protons, what can give protons is water. So it means we're going to need 2 molecules of water, isn't it? So now after getting 2 molecules of water, this calcium, nothing will happen to this calcium ion because it's just used to hold the carbonate ion. So now this water molecule, it will donate a proton to this carbonate. So but we have 2 water molecules now, which will each donate a proton. So now to form what? To form carbonic acid, right? Carbonic acid is something like this: H2CO, H2CO3. Okay, it's called carbonic acid. Okay, so it's a weak acid. So now this carbonic acid, it decomposes to form carbon dioxide plus water. Okay, so now after these 2 hydrogens have donated the 2 hydrogens to form this carbonic acid, now we will have 2 OH minuses left. Okay, so now this is the equation that we will have. Okay, so you may also argue and say that, okay, we can simplify this equation further by saying, because I have 1 mole of water, I have what? 2 moles of water, can cancel this side and then I will be left with another one. So meaning I will have calcium carbonate plus water plus 1 water, giving me what? plus water, giving me calcium 2 plus 2OH minus plus carbon dioxide, right? So if you check this, if we try to balance, we have two hydrogens on the left, we have two hydrogens on the right, we have four oxygens on the right, we also have four oxygens on the left, one carbon, one carbonate, one calcium, one calcium. So it is balanced. Okay, so it will be like that if you simplify it any further, but I don't want you to simplify it to this point. Why? Because I want you to understand that because calcium carbonate can accept two protons, so we will need two molecules of what? Of water, you see. So but this is also this is the net reaction for this one. Okay, so now let's check another bulletin. Okay, so how to prepare a standard solution. Okay, so first things first. Okay, first thing first, what is a standard solution? What is a standard solution? So what is this standard solution? What do you think it is a standard? What do you think is a standard solution? Okay, so did you get the answer? Okay, so now this standard solution, it is a solution that we know its exact concentration. Okay, it's a solution that we know its exact concentration. So a solution with known exact concentration. Okay, so we are sure of the concentration of a standard solution. So we have different types of standard solutions, which I'm not really going to define for you to know, but we have two types of standard solutions. Okay, so in we have primary standard, we also have a secondary standard. Okay, so a primary standard is what contains of a pure compound. Okay, pure substance. So usually the primary standards, they're the ones that are being bought from the labs, such as Sigma Aldrich, you know, and other chemical companies. So, and then now this secondary standard, they're going to use the primary standard to what? To create a secondary standard. Okay, so now because they will use this primary standard to create this one, so this secondary standard is not really pure as compared to this one, and this secondary standard is more reactive compared to the primary standard. Okay, and this one, it is used depending on whatever reaction you want to perform, also used in analytical chemistry in titrations. Most of the solutions that we use, they are secondary standard, okay, but what you have to know is that they are standard solutions, okay. And a standard solution, it is a solution with an exact known concentration, okay. So and standard solution, it is used to determine the concentration of the unknown secondary of an unknown solution. So now if I use a solution with a known concentration and I'm trying to determine the concentration of the other solution, so I'm treating the other solution with unknown concentration as what? As a secondary standard, because when I know its concentration now, I know that, oh, it is a concentration that I've determined experimentally, which is not exactly pure because there's margin of error, there's a plus or minus of error that is there. So it's not really pure. That is why I say secondary standard is not the real Magoya, but primary standard is the real Magoya. Okay, guys. So now, how do we prepare this primary standard? Okay, I will try to link a video of a practical where they prepare this primary standard for you. Okay, I will link it in the description of this video. Okay, so but what they do for acids or bases that come in solid form, right? That come in solid form. First of all, we have to weigh the solid. Okay, we have to weigh the solid. After weighing the solid, what do? We transfer the solid quantitatively into a volumetric flask, okay. And then after that we add distilled water and fill to the mark of the volumetric flask. Okay, so now there are conditions of preparing a standard solution, right? So so here what I'm talking, I will draw like just schematic diagrams to show what I'm talking about, although you will see it in the description. Okay, so so we use what we call a chemical balance. Okay, a chemical balance is like a scale for weighing compounds. Okay, it looks something like this, and then you put your weighing beaker here. Okay, so here the numbers, you can read 1.2 grams. Okay, so now after weighing on a chemical balance, okay, okay, so for very accurate results, there is this sophisticated chemical balance called the analytical balance. It has some windows, you can close it to, you know, to prevent vibrations from disturbing the accuracy of your results. Okay, so now after weighing this solid in here, this solid inside this weighing beaker. We transfer the solid into what? Into a volumetric flask. So volumetric flask, it is a glassware. It is an apparatus that we use to prepare solutions. So because it has a smaller neck, we use what we call a funnel, glass funnel. Okay, we use what we call glass funnel, and then we transfer the solid through the glass funnel into the volumetric flask. Okay, so now you'll see that the solid deposits at the bottom of the flask. Some of the solid will be left on the glass funnel, but what we do, we take what we some smaller than a bottle called a wash bottle, right? It's like a squeeze bottle. So you will wash the sides of the glass funnel, whereby there's still particles of our acid or base that is in solid form. Hence, I say transfer quantitatively. If you wash the sides of the glassware, everything will go into solution, and then now you'll have smaller nyana water, and then you can fill the water to the mark. Okay, so each volumetric flask has a volume. We have a 50 ml, we have 100, we have 250. We can even have bigger ones. So after you add, you swell the volumetric flask. You shake it gently, don't do it vigorously. Okay, you turn it up and down, you do it gently until everything is mixed into a solution. You have a homogeneous solution until everything is dissolved. Okay, and then now you go on and calculate what? And calculate your number of moles with your known formula of calculating number of moles. After calculating that number of moles, you are going to use this to calculate concentration. Okay, and then you take this number of moles, you put it here, divided by the volume of the solution, which is, in this case, is 50 milliliter. 50 milliliter is the same as 50 cubic centimeter. Okay, so now you get the concentration of the solution. But I have to warn you, you can only calculate the concentration of the solution from calculator if and only if the acid or base that you are using, it is a strong acid or a strong base. Okay, so you cannot prepare a standard solution by just doing this if it is a weak acid or a weak base. Why? Because a weak acid does not ionize completely in water, so the concentration that you are going to calculate, it will be wrong, because we don't know exactly how much of the acid is going to ionize in water. Okay, so it varies with temperature, and also we can't really know exactly how much of the concentration will be. Okay, so we can only make a standard solution using a strong acid or a strong base. Okay, so but if it was an acid or base that was found in liquid form, what we do, we would have to record its volume, and then we will have to dilute it so that it will be available in a larger quantity, and then we calculate concentration. We'll go to dilutions in few seconds. Okay, in few, yeah, just in a few moments. Okay, so now let me write it in full. You can only prepare a standard solution using a strong acid or a strong base. Why? Because strong base and strong acid ionize completely. Okay, so we can be sure that everything is in the solution. So theoretically we can calculate the concentration. Okay, so now we will use this later in titrations, these standard solutions. Okay, let me go back and check the outcomes. Okay, so now going to the dilute solution, how to prepare a dilute solution. Okay, so now that I have prepared my standard solution, right? I've prepared my standard solution. Okay, so now before I can even talk about dilutions, right? Let me erase this. Okay, before I can even talk about dilutions, right, I have to first uh, define what is a diluted solution. Okay, or what is to dilute. Okay, so to dilute something, a solution, it's to add more water to the solution. So if the solution contains water, let's say for example, you know those juices like Oros, for example. Oros comes in a concentrated manner. Although it comes concentrated, it does not necessarily mean it is a pure orange or whatever. So, but in that thing, there's 6% orange juice. The rest, it has some things, even water. So, although it has a smaller amount of water, it is said to be concentrated. Okay, because it contains more amount of the sugar stuff and the, you know, the stuff that they've created, more than water. So but when you are going to drink it, we say you are going to dilute it. How do you dilute it? You add the little amount of oros inside your glass, and then you add larger amount, larger volume of water in that glass, and then that oros will be drinkable. So that is a diluted solution or a dilute solution. Okay, so I can say now a dilute solution, okay, is what is a solution. Okay, so in this, because we are talking of acids and bases now, I'll say a dilute solution. A dilute solution is a solution where, or let me say which solution, which the amount, wait, let me just give a general definition first. A solution which, in which the amount of a solute, right, the amount of a solute is less. And then when I say the amount, I mean or moles, right? The amount of solute is less in proportion to the volume of the solvent. Okay, this is a general definition of dilution. So now what does it mean? The Oros example. So this is a glass uh, now there's Oros inside the class. There's Oros inside this class. So now I come, uh, I add water. So what is this Oros? This Oros is what? It is a solute. It's something that we want to dissolve in water, or something that we want to mix and make it better for us to drink, make it drinkable. So if I add water up to this mark, and you can see that this water is more than the solute. So what is water? Water is the solvent. Okay, so if the amount of the solvent is greater than the moles of the solute, we will have a diluted solution, guys. Okay, so, and a diluted solution has a concentration of less than 1. Okay, so a diluted solution has a concentration of less than 1. Why do I say that? Because concentration is given by number of moles over volume, right? So if the amount of the solute is less in proportion to the volume, then we will have what? We will have a number that is less than 1, and then we say that solution is diluted. Okay, so but now let me qualify it to acids and bases. What is a dilute acid? Definition of dilute acid. All right, so, or base, let me generalize it, dilute acid or base. But when you write it, you are not going to write it as double as it is. But knowing you, my learners, most of you would write this as it is, and you find that they've asked you about one thing. Maybe they've asked you about acid, and you write the one that is double, that includes acids and bases. So let me write it step by step so that you won't make mistakes. So now, a dilute acid, it is a solution, right, of a solution of acid, right, where the amount, right, or what, or moles of the acid is less or smaller. Okay, it's less or smaller in proportion to the volume of water. That's it. So for a base, for a dilute base, you just change where there is acid, you put base. Okay, so but I will write it anyway. So dilute base, it is a solution of a base where the amount, right, or what, or moles of the base is less, or let me say smaller, in proportion to the volume of water. You see, so they are almost the same. You just change where there's acid, you put base, or where there's base, you put acid. So now, uh, we also have another term, right? We have dilute, we have also concentrated solution. We also have a concentrated solution. Okay, so what is a concentrated solution? The general term. It is a solution in which the amount, right, or moles, right, of a solute is large, is larger in uh, proportion to the amount of solvent. Okay, so a solution in which the amount of moles of a solute is larger in proportion to the amount of solvent. You see, so now in terms of acids and bases, we say that a concentrated acid or base, okay, so this one I'm writing it double so you will separate it for yourself. So concentrated acid or base, it is a solution of acid or base uh, which uh, its amount which its amount or moles, right, is larger or just large, is larger in proportion to the volume of uh, water. Okay, so even here you should put a volume of solvent, okay, because concentration is defined as moles per volume. Okay, all right. Okay, so now that's the definition. So now I was talking about dilutions. How do you perform dilutions? So now if I have prepared my solution, right, inside uh, maybe 100 100 cubic centimeter volumetric flask, right? So if I want to dilute this, I can add, maybe I can take two smaller volumetric flasks, each of 50 cubic centimeters, 50 cubic centimeters. So I will take what I have in here and add it in here. Okay, I add well, this will not be a dilution. So if I add 50 in here and 50 in here, we'll still have the same concentration of uh, we'll still have the same concentration of the acid or the base. Okay, but if I use the same amount, the same size of beakers, right, if I use the same size of beakers, let's say also it's 100 also is 100 cubic centimeters, 100 cubic centimeters. So if I add 50 in here, 50 mil, or let's say I have another another 100 mil, another 100 cubic centimeter here, and another 100 cubic centimeter. Okay, so 1 2 3 4. So I want to add equal amounts in each. So if I can add uh, 25 cubic centimeter of acid, also in here 25, also in here 25, also in here 25, and then I fill the solution to the mark with water, with additional water. So I will have what? I will have a diluted acid or base in this form. So the concentration of each acid in here will be less than the concentration of the acid in here, because I've further added water on top of what I had. So I have diluted. So now, because when we dilute the concentration change, right? So now, for example, let's say I take a smaller volumetric flask of 50 cubic centimeters, right? I transfer the contents into a larger volumetric flask of 250 cubic centimeters. So if I transfer the contents of this solution in here to this solution, what is going to happen? I will have something maybe that is here, or less, and then if I fill to the mark with water, the solution will be what? Will be diluted. Okay, and so when the solution is diluted now, what you can keep in mind is that here is what? Before dilution, right? And then here is what? After dilution. Okay, so before dilution and after dilution. So what happens is that although the volume before and after is not the same, right? But the number of moles are still the same. Okay, the number of moles are still the same. But what happens is this: is that in number one, in volumetric flask one, let's say this is the 50 cubic centimeter flask, and then this is the 250 cubic centimeter. So if I had 10 moles, 1 2 3 4 5 6 7 8 9 10, right, in the concentrated, so they will be closer to each other. Okay, so but in the larger one, they will still be 10, but they will be far away from each other. So I will have 1 2 3 4 5 6 7 8 9 10. You see, so concentrated means that they are close to each other at each and every point inside the solution. So, and diluted means that now my moles, or the molecules of, or the desired acid or base, they will be far from each other. This is the meaning of diluted, guys. This is the meaning of diluted, and this is the meaning of concentrated. Okay, so now notice that number of moles remain the same. So number of moles n before equals to number of moles after dilution. Okay, so but the volume before, it's not equals to the volume after. You see, what about concentration? Concentration depends on moles and volume. Okay, so because the volume is not the same, the concentration before dilution is not going to be the same as the concentration after dilution. You see, so this gives us a formula that says that, oh, because the number of moles first, number one before dilution equals to what? Number of moles after dilution, right? N1 is equals to N2. We are fine. But I know that, oh, according to this formula of concentration, number of moles is given by what? By CV. So N is equals to CV, isn't it? Because if I cross multiply here, I make N subject of the formula. N is equals to CV. So now these N's, I'm going to replace them with C and V. So here I will have C1, V1, right? They will inherit the 1, the subscript 1, because of their, it's before dilution. And here after dilution, that's what? C2, V2. So what have we done here? We have came with the formula for what? For dilutions. Okay, so this is a formula that you would use for dilution. Okay, so now let me ask you a question. Let's do an example, right? Let's do an example on dilutions. Okay, so let's say a solution of an acid of concentration 0,2 mole per dm cubed was transferred okay, let me write additional information. A solution of an acid of concentration 0.2 mole per dm cube and volume, yes, and volume 50 cubic centimeters was transferred into a 250 cubic centimeter let me take 100 so that you can see something. Was transferred into 100 cubic centimeter flask and filled to the mark with distilled water. This is the statement, right? Now calculate the concentration of the final solution. Then they say 3 marks. What are you going to do? So let's look at the question and the statement. The statement says a solution of an acid of concentration 0,2 moles per dm cube and volume 50 cubic centimeters. So this is the information for what? Before the solution had a concentration of 0,2 and a volume of 50 cubic centimeters. So it was transferred into a 100 cubic centimeter flask and filled to the mark with distilled water. So what happened is this is what I showed here. So it's coming from this one, then it was added to the other one, but the other one is 100 and this one is 50. So and then now filled to the mark with distilled water. So because it's filled to the mark with distilled water, so tells us that, oh, now the new volume is what is 100 cubic centimeter, the new volume, which is the final volume. So the information that we have, so before dilution we have C1 and we have what, we have a V1, right? And after dilution, what do we have? We have C2 and what, and V2. So here C1, they've given us 0.2 mole per dm cube. Then V1, how much do we have? We have 50 cubic centimeters, isn't it? And then C2, they say calculate the concentration of final solution. We don't have C2. What about V2? V2, we have it. How much is V2? V2 is what? It's 100 cubic centimeters. Okay, so how are we going to calculate C2? We use the dilutions formula. C1 V1 is equals to C2 V2, isn't it? So now I'm looking for what? For C2. So I can see that, oh, if I make C2 subject of the formula, I divide both sides by V2. So C2 is equals to C1 V1 over what? Over V2. You see? Over V2. So now, how much is C1? C1 is 0.2. How much is V1? V1 is it's 50 cubic centimeters over V2 is what is 100. Notice that I did not convert the units of these volumes. Why? Because I have volume on the numerator and volume on the denominator, so the units are going to cancel out. Okay, so if I can convert it, I will still get the same answer, but time, when you are writing in an examination, you will find that you don't have time. You will have wasted a good 5 seconds or a minute of converting and writing it down. Okay, so you can just substitute them as they are, and then the units will cancel out. But be careful, if you only have volume in the numerator or denominator, you must convert it. But if you have two volumes that divide each other, you don't have to convert it. Okay, so now okay, I cannot find my calculator, so I guess we'll use this one. So 0.2 multiplied by 50, how much? It's 10. So now 10 divided by 100, how much? 0, 0.1. You see? So the answer now is what? 0.1 mole per dm cube. You see? So what happened here? Initially my concentration was 0.2. Now final, after dilution, my concentration is what? Is 0.1. So you can see that when we dilute, the concentration decreases. So dilutions leads to decreased concentration, but the number of moles remain the same, right? As I have shown you here, and it's what give rise to the formula, the fact that number of moles remain the same. Okay, guys, let's go back to the learning objectives and see if we have covered everything we said we will cover. Oh yeah, so there isn't much about dilutions that will scare you. That's all there is to it about dilutions. Okay, guys, uh, I love you. Thank you for tuning in. Don't forget to like, share, and subscribe. And those who get these videos from others, even if you did not watch the video on the portal, just go and subscribe and like. Okay, it helps the channel. So that way I'll keep on making more content if you subscribe and like. Okay, thank you guys. Keep well.